the next talk is going to be on quantum state complexity of formal languages, and it's going to be presented by Tomoyuki Yamakami.
Yeah, thank you. Thank you very much. Well, this is the joint work with the Marcus Jagra. He is now in Paraguay. He has been in my postdoctoral fellow for 2 years, and this is the joint work with him. So before starting my talk, I just let you know a little bit about where the University of Fukui is. A couple of people actually asked during this conference, where is Fukui? So I just give you some hint where it is. So it's not that in a big city somehow. First of all, I just explained the basic idea about Japan. And Japan consists of 47 so-called prefectures. It's like a province or states or whatever it is called. One of them is Fukui Prefecture. That's located around somewhat in the middle part of the whole Japan. And as you see, Tokyo is around here. It's a 3 hours and 30 minutes train ride. And Osaka and Kyoto, Kyoto is very close to Osaka, but that's just 1 and say half-hour train ride. So that's the way the Fukui Prefecture is. The Fukui Prefecture looks like more like a tadpole, and the Fukui City, where the university is situated, and that is actually located somewhat at the middle of the head. Okay. So we just get back to our work. First of all, this talk is about the quantum computation, and particularly the state complexity that measures the complexity of the languages. But here I'm using quantum finite state automata instead of the standard, so-called classical finite automata. And the basic property of this state complexity, well, because I'm using the quantum finite automata, I just call it the quantum state complexity instead of the state complexity on quantum finite automata. So make it short. So I'll explore the basic properties, and then I'll show you some techniques to show the law of this quantum state complexity. Okay, so the motivation. Why do we need quantum? Because, as you know, the computers that we are using, so the people, the researchers are working on the quantum computation is called the classical computer. It's not really classical in the sense that classics in the music, but the current computer have some problem in the future because the people actually manufacturing smaller shapes. The computers getting faster and faster, but there might be some limitation, so that you can't make it faster after that limitation and make it smaller. So what do you want to do? So we have to look into something else. So one possibility might be coming from the realization of the fact that the information is a physical object. So why don't you use it? Right? The nature is governed by the quantum physics, so that the quantum physics would be one of the best choice. So I just give you some idea about quantum computation before getting into my work with the models. So the qubit, the standard bit is, as you know well, 0 and 1. Quantum bit, or we call it a qubit, like a quantum bit qubit. The qubit is a very different. Somewhat the linear combination of 0 and 1. And we use this special notations, the Dirac notation, to represent classical bit 0, and this is 1. So quantum bit is some kind of a mixture. Physically speaking, we will just look into the small, tiny particle, and the particle is always spinning. So at the end of the spin head goes upwards, so we just represent this. This means we are actually representing the classical bit 0. But then if the spin head looks down, then that corresponds to the classical bit 1. But you know that the spin head can look directed in any possible direction. So that means the one qubit possibly contains an infinite amount of classical information. For example, how can I represent that kind of qubit? There is several ways. One simple way is to look at the atoms. Atom is usually consists of the nucleus and electron. If the electron some orbit, circle the nucleus on some certain orbit, fixed orbit. They can't go randomly somehow. So supposing that we have two fixed orbits, and one particular electron, one electron can possibly circle around the two orbits at the same time. So that's the beautiful thing about quantum mechanics. So that represents in the mixture of 0 and 1. Well, this is just the kind of pictures people like to watch. So another thing, the very peculiar about quantum mechanics is that observation or measurement. We have to look at the result of this quantum bit. So, but what we have to get the information out of this qubit, we have to take a look at this particular particle. But the particle is a really tiny thing, and the seeing means that you have to actually hit the photon into that object, and then you have to receive what the outcome of this photon. Right? But the photon is also a very tiny object. So that if you just throw the bowling ball against the ball, then the ball will not be staying there. So that you can't get the same reaction as you actually throw the ball against the wall. So the result is not reliable in some sense. So we call it a collapse. So the quantum state collapse by the measurement into either 0 or 1, nothing else. But then we will get either 0 or 1 with some probability, depending on this, the spin head is closer to 1 or closer to 0. Okay, so that one single trial does not give you the full picture of the qubit, because you only get either 0 or 1 accidentally somehow with some probability. So another peculiar thing is the correlation among the two qubits. So suppose you have two qubits, and this one and this one. So you can actually make them related in the sense that, for example, this particular state, so it's called an EPR pair. The first E stands for Einstein. And so whenever you actually observe this in the first qubit, and you discover 0, then the second one automatically becomes 0 without even looking at it. So that's actually some sort of transmitting information from one qubit to another without sending anything. So that's this is actually the source of so-called the quantum transportation. So you're just transporting one person to another, far away, without even sending anything. Okay, so this is just a little bit about the quantum information theory. Now we move on to the quantum finite automata. I start with the probabilistic finite automata, so that's much easier to understand for you. So the probabilistic automata is something like this one. So I just include the two end markers. Yeah. So so we'll call it PFA, so one way or either two way. So head moves either one way or any way. So the formal definition of the PFA is the 6-tuple. And the important thing is the probabilistic transition function. Transition function is somewhat similar to the non-deterministic transition function, but you have to assign the probability into from one state to another. You're actually moving from one state to another state, and then that has to be happening with some certain probability. And the requirement, well, because this is all about the probability. So requirement here is that all the probability have to sum up to 1, right? So if you actually can have two choices from Q0 initial state moving to Q1 or Q2, then you have moved to Q1 with 30% of the chance, and another one has to be 70%. And And slightly different from the standard definition of the cut point formulation, I just use the bounded error formulation. So this is slightly different. To think about it in the computation of the probabilistic finite automata, starting with an input x, and then we have a bunch of the computation paths attached with the probabilities being attached. And some of the paths end up with rejecting states, and another ones actually end up with an accepting state. So we simply calculate the probability of getting it rejected and getting accepted. The bounded error means that we have either one of those things. Either we have reject input with high probability or accept input with high probability. In that case, 1 minus epsilon, and epsilon is an error bound chosen between 0 and 0.5. So now we move on to quantum finite automata. Quantum finite automata is very similar. Well, if you just look at this page, you can't see the difference. But the few difference appeared here. Instead of using the probabilistic transition function, I'm going to use the quantum transition function. So the quantum transition function takes the any complex numbers instead of just a number between 0 and 1. And the requirement for this quantum transition function is described in the following way. So we'll define the so-called time evolution matrix. This is the matrix associated with this delta. Basically, this is the linear transformation from one configuration. Configuration means a pair of inner state and the location of the head on the input tape. So you just change this configuration from one to another. So that is described or governed by this matrix. So this matrix has to be unitary. So that's the requirement for the quantum computation. Unitary means that U multiplied by U transpose conjugate has to be identical. In other words, you actually preserve the norm of the vector. That is the same definition. And also we take the measurement operation to look at the final result, and then we have to tell whether we have accepting state or rejecting state, or just computation is still going on. So instead of describing in the two-way quantum finite automata, one-way quantum finite automata is much easier to define. So I just give you a more precise definition about QFA. So we have time of evolution matrix, as I said, but in this case, we don't care about the location of the head, right? Because the head always moving in one direction. So the configuration is exactly the same as the inner state. So the time evolution operator is based on what you're reading now, and then how to change one state to another with some complex numbers. And projective measurement, that is, as I said, we have to check whether we are currently in accepting state or rejecting state or non-halting state. This is also called the von Neumann measurement. And the computation goes like this. You start with the initial quantum state that contains only initial state. So now you apply this time evolution operator, the matrix, and then you will get psi 1 from psi 0. And then you have to apply the measurement. The measurement actually can reach to 3 possible states. And one of them is accepting state, another one is the rejecting state, another one is non-halting state. So we calculate the probability of getting into here is just the square norm. Oh, sorry, I forgot the square here. The square norm of this vector. And as the computation goes on, whenever there is something left over after the getting into the accepting or rejecting states, and so on. And when read the end marker, then the computation paused. So now I'm going to introduce the complexity class called 2BQFA. Some people call it just 2QFA. So this is the collection of languages recognized by the 2QFA with some certain error bound. And M uses only coefficients or the complex numbers taken from K. The K is the subset of complex numbers. And the requirement 2 and 3 are very important. So all the words belonging to L have to be accepted with high probability. In this case, 1 minus epsilon. And all the other strings have to be rejected with the same probability. At least 1 minus epsilon. So this is the definition of the 2BQFA. The peculiar thing about it, the quantum finite automata is that one-way QFA is not really powerful enough. And that is strictly the property contained in the regular languages. This is actually the set of regular languages. But then if you take the two-way QFA, the power exceeds the regular languages. So now we move on to defining the quantum state complexity. So we'll take a look at it in the past literature. So-called traditional or standard or conservative state complexity concerns about just a minimal number of the inner states used by the machine that recognize the language. That means working on all possible input strings. The early result concerning the state complexity is probably Binus and Fravos. He is over there. For fixed given prime numbers, we'll define it in L sub p. L sub p is the unary language, 1 to the n, and n is divisible by p. So if you use the quantum finite automata, it takes just all of the log p inner states to recognize this particular language. But probabilistic finite automata, well, you need exponentially more. That means you need at least p inner states, so that the gap between them is exponential. So a whole bunch of the other people, including him, he is over there, and other people, those people actually discussed the preciseness or state complexity of the quantum finite automata. From a different point of view, Binus, Nayak, and Kashmir, and Zirani, they actually argued in the following, got into the following result. L sub n is a fixed number here, and consider the collection of the W0. W is taken from is a binary string, and the size of this input is at most n. So that you only focus on the string of the size at most n, so n is a fixed number, right? So then the DFA use only all of n inner states to recognize this language. But the quantum finite automata in a bounded error case requires 2 to the n. So that the exponential gap again, right? So now you see that the difference between the first slide and the current slide. So you can't really say that the quantum finite automata is much more concise than the classical finite automata. It's depending on the case by case. So now I'll take the second definition as our basis. So that I'll just rephrase it. So that the machine, or the given language L, and we will just slice the language, the sigma star, into strings of length n. And we are only interested in this small window, not looking at the whole entire sigma star. And then we will define the whole thing. The machine recognizes L at n, so n is a fixed length. with error bound epsilon using k. K is the amplitude set. Oh, I'm sorry, I forgot to mention that the amplitude is the number associated with the transitions in a quantum finite automata. So that all the strings in L sub n, are accepted with high probability, and all the other strings within this small window are rejected with high probability. So that's the definition of the quantum state complexity. So we don't care about the other strings. Okay? So the state complexity of this particular machine is the number of the inner states. Similarly, we will define the following thing. So we just simply looking at all the string up to n. Not only just looking at the length of n, but also up to n. Then we will define the similar thing. So here, we will use recognize up to n instead of up n. So that's the only difference. So now we'll introduce notation. One QSC, one-way quantum state complexity using the amplitude set k and an error bound epsilon of L of at n. That is defined to be the minimum number of an inner state needed to recognize L at n using one-way quantum finite automata. Similarly, we'll define two QSC using two QFA instead of the one QFA. In analogy, we'll use the at most n instead of at n. So we'll play with those four notations. A simple relationship between those at n or up to n, two types of definitions. Clearly, up to n state complexity is larger than at n state complexity. So simple example here is that, so you remember the definition of 2b, the b stands for the boundary error, b QFA. So the state complexity of this particular language is constant. But we don't know whether the other way around still holds. So that is quite different from the deterministic case. So now we move on to, and I'll just explain the very few basic properties of this state complexity. So upper bound of the state complexity at n is, well, the size of the alphabet to the n plus 1. The minimum one is 1 because we have the initial state. So then this state complexity is somewhat close down to complementation because we're actually using bounded error, so two-sided bounded error. So it doesn't matter. We just repeat the acceptance and rejection. That's it. And so concerning the amplitude, well, the complex numbers are a little bit hard to deal with. But you can actually switch to it real numbers at the cost of just the multiple factor of 2. And the more precisely, the relationship between it at n state complexity and up to n state complexity. So we have an exponential gap for some certain language. But the language is very simple as regular language. So exponential gap here. So now let me explain the main result. So first one is about the union and the intersection. So first thing I just tell you about it, one-way bounded error QFA. So this particular complexity class is not falls down to intersection or union. So it's not really nice as the regular languages in context free. Well, context free is that is not close down to intersection anyway. Okay. So in terms of the state complexity, so this is actually the bound. So we have the L1 language L1 and L2, and the state complexity of an L1 is K1, and the L2 of state complexity of an L2 is K2. Then the union or intersection here, union or intersection of the two languages is bounded by this. It's a multiplication of K1 and the K2 times order of n. So it's a little bit big, but I haven't really thought about it in the long case, so that I'm not sure this is really tight. So this is just by the direct simulation. So you just take a look at the minimum quantum state automata and then just combine them, and that's it. But then if you look at it in a two-way quantum finite automata, situation is something different. This has to be 0, so the error is 0. So if you take BQFA language, L1 and L2, and then consider it in the union or intersection, the state complexity associated with those operation is 2 to the log n squared. Now, again, so I'm not quite sure whether this is tight or not. So next topic is advanced computations, right? Do I have to okay. Okay. Advice is the external information, so that you just simply give the information directly to the finite state automata. So an automata take the standard input and advice given by the human or whoever, and then they start computing. So here. My way of giving advice is something like that. You have only one input tape, and then I split this tape into 2 tracks. And the upper track contains the standard input X, but then the lower track, we just give the extra information. But the tiny thing. So this advice is depending on only the size of the input, not the input itself. So, for example, if you're working on a binary string, right, and then you actually can take the size n binary string. There's all possible strings associated with length n is 2 to the n, but you only have one advice. So the head reads the both symbol at the same time. So that the upper track contains the standard input, and the lower track contains advice. So that you just the head, the machine read the input, piece of input and the piece of advice at the same time, and then move on. So we just simply add that kind of an advice mechanism into one BQFA and two BQFA. So that is called an advice computation. So the definition is pretty much simple. Going back to this one here, right? So you just simply give one advice depending on the size of the input, and then the machine actually accepts if and only if then X is in L. And the 2A is the same. So now the state complex of advice computation is something like this one here. So if you take the language belonging to the 2 BQFA / n, so that you actually you are getting the advice, right? And the state complex of this language is order of n. But if you don't have advice, as we have seen, the state complex of the language L is constant. So that we have n gap. So in some sense, length n advice is somewhat equivalent to the order of n extra inner state. So now, by the way, regarding to the advice, there is a very nice technical lemma called the swapping lemma. This is actually information only applicable for the context-free languages, but the regular language, the swapping lemma for a regular language is much easier. So the swapping lemma says that well, in a given context-free language, then there is always a swapping lemma constant, and that satisfies the following condition. So take n that is smaller than at least 2, and then take any s as a subset of the L, but the length is limited to n, and then take the j0 in the case and some number. And if s satisfies in a certain condition, then we can do the following thing. So I just show you the picture here. So there exists two strings, x and y, of the length n in S. Okay, S and S is a subset of L, right? And then we just swap the middle section of two strings. Then the resulted strings also belong to L. So that's very nice swap. That is very useful. I just and this is just an information. So if you're interested, then maybe just take a Google search to look at it in the swapping level or context-free language, and you can actually hear the stuff. Or the paper is actually in the archive. That was written a long time ago. Anyway, so we'll just go back to the last result. So that is about an approximate matrix rank. So we fix the language of the alphabet sigma, and then we'll consider it a characteristic matrix. That is the entry, xy entry of this matrix is either 1 or 0. When xy belongs to L, the matrix entry is 1, otherwise 0. So that you have 1, 0 matrix. And we restrict this matrix, so that something like this one here. So this is a huge, infinite dimensional matrix. But now you just slide them. Okay, thank you. Yes, slide them out according to the xy, size of xy is at most n. So you just cut the portion. So we'll define it as the terminology epsilon approximation. So I just give you a fact here. So take a look at this one here. So consider the algorithm A or finite state automata or whatever, some machinery. And then you just form the matrix consisting of P sub xy. That means the acceptance probability of this algorithm on input xy. So you just simply attach all the acceptance probability as the entry of this matrix. So this matrix, epsilon approximate this characteristic matrix if and only if this algorithm recognizes this portion of language with error probability epsilon. So more precise definition about the epsilon approximate means that the infinite norm of the difference between two matrices is at most epsilon. So now, pretty much close to the end, the theorem I got using this approximate matrix rank is that the lower bound of the state complexity. The state complexity, so for given L, okay, and the given function, state complexity of L at most up to n is lower bounded by this number. It's very complex here, but so this is kind of very interesting. But a little bit, the tricky part is because I have to deal with the probability, right? The error bound, so that we have to take some tiny gap here, and so that appears here and that kind of stuff. But that's just some small things. But the important thing is the state complexity is bounded lower bounded by the square root of the rank. Well, what is this rank? So this is the actually minimum rank that epsilon approximate that characteristic matrix. So this is called the approximate matrix rank. And as a corollary, well, the theorem itself is very interesting from the point of as a technique and showing the law. But corollary is also very interesting. So that gives the result like this one here. The L stands for the deterministic log space complexity class. That is not contained by 2 BQFA whenever the time is bounded by this, but exponential somehow. So even if you have the exponential amount of time using the 2 head moves, but still you can't recognize L. So 2 BQFA is not that big somehow. Okay, so now I'll show you, some future challenges. There are tons of the problems, and I just started this quantum state complexity issue. For example, one of them is the we need more general property like closure properties and so on. And as I mentioned that we don't know about the closure property of 2BQFA under intersection and union. So why don't you try to prove that in terms of state complexity, right? So that's the initial motivation of me studying with this argument. Okay, so the third one is discover new techniques. And I presented one technique, but it could be more, right? So, for example, the diagonalization technique and so on. Well, thank you for listening. And I'm happy to take it.
Are there any questions? Any?
Just for clarification, you had a mysterious formula for Q prime in terms of a rational fraction or rational expression. Where did that come from?
Which one? This one?
No, the one for union.
Oh, union. Okay. Just a second. Oops. This one? Oh no.
No.
Previous one. Oh, this one.
Yeah.
Okay. It's just a direct simulation.
Direct simulation.
Yes. So I tried to make it, as efficient as possible. So I just made a small, tiny trick. It's not just simply to combine them. That doesn't work for the quantum computation. So then I had to make some small changes. So that's why it will get this kind of strange, the error probability appears.
Thank you. Are there any other questions? Then let's thank the speaker once again.